Good morning, students. Am I audible to you?
Yes, sir.
All right. So we'll continue with what we were doing in the last class and then move on to the next topic in today's class. So that will be the agenda. So in the last class, we have seen one method of analyzing or studying a two-dimensional heat transfer system, a system where two-dimensional heat transfer is possible. So I have told you that there are three methods. One is the analytical method, which is for which you need to be very good at mathematics, especially the partial differential equations and their solutions. It may not always be possible, but if it is done, well and good. The second method is having a limited application. That method is called as the graphical method or the method of using the flux plot. That method is suitable for systems where the boundary conditions are a combination of constant temperature or uh, adiabatic boundary conditions. So when the boundary conditions are one of these two or a combination of these two, we can attempt a graphical solution. So that means if there is a radiation boundary condition or a convective heat transfer boundary condition or a constant heat flux boundary condition, we cannot use it. The third one is the numerical methods, which we shall see after CAT2. That is a quite interesting method, quite useful method, and most of the softwares use that method only. So as of this class, we will continue with what we are doing in the last class. In the last class, we have seen what is the graphical method, we have seen what is a shape factor, and we have seen how to derive the shape factor from the graphical method. Now, we will go ahead and solve a similar problem where there is a situation of a two-dimensional heat conduction, how to apply the graphical method and solve it, and also uh, derive the shape factor. We have seen yesterday how to derive the shape factor from the graphical method, but now from first principles, how to derive the shape factor, we will also see that. Okay, so I will share my slides now. Okay, so this is the problem we can take up for starting today's class. Here you have a structure consisting of a metal walls 8 centimeters apart with insulating material between. Ribs 4 centimeter long protrude from one wall every 14 centimeters. Okay, they can be assumed to stay at the temperature of the wall. Find the heat flux through the wall if the first wall is at 40 degrees and the one with the ribs is at 0 degrees. Find the temperature at the location A. So basically, we are given some geometry, some temperature conditions, and we are told to find out the heat flux. Heat flux is one way of expressing the heat transfer. Okay, so heat flux is something we need to find, and also we need to find the temperature at a given location. So the figure is available in this. So this is the geometry. This is the two-dimensional geometry. So we have one wall here at a temperature of 0 degrees Celsius, and this wall is also having a rib. This protrusion, you see, this is the rib. And there is another wall here, which is at a temperature of 40 degrees Celsius. So this is the geometry. So without the drawings, this geometry will be something with something like this. So this is the bottom wall, this is the protrusion, and this is the top wall. So this one is at 0 degrees Celsius. This rib also is at 0 degrees Celsius, and this one is at 40 degrees Celsius. Okay. So after construction, you have all this flux plots as you see, all the lines, isotherms and adiabats as you see. So in this, we are asked to find out what will be the rate of heat transfer. Now we know that the heat transfer takes place from high temperature to low temperature. So you see this side is 40 degrees and this side is 0 degrees. So heat transfer takes place in this direction. This is unfortunately there is a rib here, therefore it may not be exactly a vertical line, it may be a curved line. So we will have to take care of that. So this particular geometry has been given to an expert and he has prepared the flux plot. So your job is not to prepare the flux plot. Flux plot is already available. So for the given geometry, you are given the flux plot. So you have to find out what is the heat transfer and what is the temperature at point A. You see point A here. Point A here, this point, at this point, what is the temperature? That is the question we are being asked. Okay. So now you see how the flux plot is drawn. This is a high temperature surface. This is the low temperature surface. So heat transfer takes place here, and you see here, these are the lanes in which the heat transfer is supposed to take place. And since this side, the left side is symmetrical to the right side, we are not separately drawing anything on the left side, only the right side is drawn. So whatever we calculate here, from that we will understand what are the quantities. Okay, and you see here the temperature between 0 degrees and 40 degrees. This also is broken up or split up into certain number of parts. So this is according to the isotherm. So these lines are isotherms, and these are adiabats. So heat transfers through the adiabats. Okay, in between the space between the adiabats. Okay, so to start solving this problem, basically we need to find the shape factor. So shape factor, if we know the shape factor, we know that Q is equal to S K delta T. So this is the basic formula. Now, do we have the conductivity? Yes, we have the conductivity as 0.12. So K is given as 0.12. So that is fine. So what we need to, delta T is how much? Delta T is 40 minus 0. Minus 0. 40 degrees Celsius. Okay. So all we have to do is find out the value of S. So in yesterday's class, we have seen S is equal to what is the value in terms of the flux plot? M by N multiplied by L. M is the number of lanes through which the heat transfer is taking place. N is the number of temperature steps, and L is the length. Okay. Now, if we can count here, you see these are the lanes in which the heat transfer is taking place. So, 1, 2, 3, 4, 5, 6. So, in 6 lanes, flow is taking place. So, M is equal to 6. Then, the temperature steps, you see, from 0 degrees to 40 degrees Celsius, the temperature has been split into 1, 2, 3, 4, 5, and the sixth one is not complete. It's actually 5.6. So it's only 0.6 times of the earlier sizes. Therefore, this is as the number of temperature steps are 5.6. So you can say N is equal to 5.6. Similarly, the number of lanes, you see 1, 2, 3, 4, 5, 6 are the full lanes, but there is 1.15 lane, small lane is available here. That also must be counted. So 6.15. So M is 6.15, N is 5.6, and we need to know the L. In the problem, we are not given the length L of this. So in such case, what we can do is we'll assume let L is equal to 1 meter. So for 1 meter length of this particular geometry, what will be the heat transfer or what will be the heat flux? That is what we will be calculating. So S is M L by N. So M is.
So what is the 2.1 in the diagram?
This 2.1. This is the
Yeah.
location of A. We'll come to that. M is 6.15. N is 5.6 and L is 1. Okay. So this will be 1.1. Okay. 1.1 meters. Now we'll find out the value of Q. Q is equal to 1.1 multiplied by 0.12 multiplied by 40. So this will be 5.27 watts. And since we have considered this as for 1 meter length, we'll say per meter. So this is the answer, or this is the heat transfer, or this is the flux. Usually the flux units will be, flux is represented as Q double prime and will be measured in watts per meter square. We don't have the area here. Therefore, we leave it at this. We can compute per unit length and leave it. So this is considered as flux as a watt per meters. Okay. Now the next question in the problem is find the temperature at the location A shown in the figure. So you see the location A. Location A is midway between the 0 degree phase and 40 degrees phase. Okay, so at this point, what is the temperature that is being asked? Now, if you look at this entire region, a temperature difference of 40 minus 0 is 40 degrees. This 40 degrees Celsius range, this entire range is 40 degrees Celsius. Okay. This range is split into 5.6 steps. Now, the point A, if you count from here, this is 1, this is 2, and this is, as it is given, 2.1. It is between 2 and 3, but it is close to the second segment. So it is with 2.1 as marked here. So for 5.6 steps, the temperature increment is 40 degrees. So it is rising, isn't it? From 0 degrees to 40 degrees. So in 5.6 steps, the temperature rises 40 degrees. So in 2.1 steps, how much is the temperature rise? So let us write this. For 5.6 temperature increments, delta T is 40. So for 2.1 temperature increments, delta T will be 2.1 by 5.6 multiplied by 40. So this is 15 degrees Celsius. Okay. So you see, with the flux plot, see, to solve this in a CFD, or to write a code for this, or to solve this analytical solution is most likely impossible. To solve it in a CFD, it will take setting up the case and discretizing it and then running it. It will take at least an hour. Now, with this flux plot, but of course, flux plot is not easy to obtain. But once you have this flux plot, you see, we could easily obtain the amount of heat transfer, and also we could determine what is the temperature at a given location. So likewise, you can determine the temperature at every point in this entire region, provided you repeat this calculation. Okay, so this is the way in which the flux plot is used, or the graphical method is used to estimate. Is it clear? Are you able to understand this?
Yes, sir.
See, the difficulty with this graphical method is to come up with the flux plot. And the flux plot, as I told yesterday, it has to be done very carefully, and you have to make sure that this perpendicularity is maintained. Otherwise, it will be, these things must be maintained. So if that is done, other things will be quite easy. So as I said, this needs a person with a lot of experience and skill to do it. So that is how we have to do it. We'll go to another problem where you see, yesterday I have shown this table where you have the shape factor, the analytical solution of the shape factor. So if you can calculate this shape factor using the simple formulas, then you will be easily able to find out what is the amount of heat transfer, and later we can also find out what is the amount of the temperature at a particular location. So using that concept, we can, so you may ask, how did we come up with these things? Such things we cannot come up, see equations involving logarithms and trigonometric functions, you cannot come up with the flux plot, right? Using the flux plot, we could find out the numerical value of the shape factor, but not any analytical equation for the shape factor. So how did we get this shape factor? Demonstrate now. Okay. The problem. Simple. Calculate the shape factor for a spherical shell. That's all. There's a spherical shell. Are we familiar with spherical shells? Do you know what's a spherical shell?
Sir, a hollow sphere.
We have seen earlier, right? So spherical shells are known to us. See something like this. This is spherical shell. This is R1. That is R2, and it is sphere. And we have considered the one-dimensional concepts of this spherical shell. We have derived equations for the heat transfer and the temperature distribution in a spherical shell. So you can refer to earlier parts of module number 2 to get the equation of spherical shell. So the starting point to solve this problem is to first take up the differential equation of a sphere. So you have dou by dou r of r square dou t by dou r is equal to 0. So this is the heat conduction equation in spherical coordinates with no r term, sorry, no z term, no phi term, sorry, not z term, no phi term, no theta term, no heat generation, and also no transient term. So only one term is there. Now, because this is in one dimension, what we can do is this is d by dr of r square dt by dr. Okay. Now, again, we to solve this problem, this is equal to 0. To solve this problem, we will have to integrate it. Since this is d square t by dr square, we will have to integrate it twice. Once we integrate it twice, you will get two constants, C1 and C2. So this C1 and C2 can be obtained by using the temperature boundary conditions. Let us say at this point the temperature is T1 and on this surface the temperature is T2. So using the values of these boundary conditions the boundary conditions are at R1 T is equal to T1, at R2 T is equal to T2. Okay, using this boundary condition, we should be able to evaluate the values of C1 and C2. So using that, we will be able to find out the temperature distribution inside this particular spherical shell. So using that, we have seen in, if you refer, we have done this already, so I will not do it again. So what you can do is you refer to page 53 of the data book. You will see that for a spherical shell having inner radius R1, outer radius R2, and inner temperature T1, outer temperature T2, the temperature distribution or the resistance, the conduction resistance is given as 1 by 4 pi k 1 by R1 minus 1 by R2. Okay. Now you know the R value, so we can calculate Q as delta T divided by R. So delta T divided by 1 by 4 pi k into 1 by R1 minus 1 by R2. Okay. Now, we will bring this this thing to the top. So what will happen is 4 pi k delta T by 1 by R1 minus 1 by R2. Or further simplifying, you take 1 by LCM, 1 by R1 minus 1 by R2. So this R LCM will be R1, R2, which can come to the top. So this will be 4 pi k R1, R2 multiplied by delta T divided by this R2 minus R1. Okay, now this is the value of Q. Now in terms of shape factor, we can also write Q as Sk delta T. So we have two equations for Q now. One is this is the one which we derived from the differential equation, and the second equation as per the definition of the shape factor. So if you compare these two equations, this delta t and delta t is same, k and k will go. So what remains is s here, and what remains is 4 pi r1 r2 by r2 by r1. So therefore you can write s is equal to 4 pi r1 r2 divided by r2 minus r1, which is the answer. So you see here, the analytical values of the shape factors can be derived using the analytical solution of the conduction equation for each and every case. So we have seen that there are several cases here. Here you have a square channel, and here you have a different section. Here you have a horizontal cylinder buried in some region. So on here, you have two pipes buried in certain medium, so on and so forth. So all these equations are first solved using the conduction equation, and then equating it to the heat transfer equation involving the shape factor, you can find out the value of the shape factor. So here, what I have done is I have taken a very simple problem here, a problem for which we already have the solution. So for the step-by-step solution of this particular problem, refer to the earlier notes. The final result is given in the page 53 of the data book. So you can see that the resistance is given using Q is equal to delta T by the resistance, that formula. We can evaluate the value of S. Okay, so in this way, we come up with this type of shape factors in analytical, using analytical methods. Okay. So with this, I would conclude this two-dimensional analysis using graphical methods in this module number 3. This particular problem number 4, I leave it to you. You solve it. You will have to take up, or you will have to go to the chart here. See here, this chart, and solve this particular problem. You have to select the appropriate one and then solve the problem. Okay. Leave that to you as an exercise. We will move on to the numerical solution part. I will take up this. This is quite interesting and this is time consuming. So I will take it up after I finish after you finish CAT 1. So until then, we'll skip this particular part. This 5 to 6 slides. Then we'll come to what is an unsteady state heat transfer. So until now, what we have been doing is to study the steady state heat transfer. So where things are not changing with time. So most of the engineering equipment that we get to see in day-to-day life, they operate on steady state conditions over a long period of time. So once you start something and let it reach steady state, it will continue to operate like that. For example, if you take a thermal power plant, the starting of the thermal power plant could take about 15 hours. But once it is started, it will continuously operate at a steady state for a period of a few months. So that steady state operation period is quite long. The unsteady state operation period is short. But in some cases, the unsteady state operation also is important. Therefore, it is, example, in burning of a fuel. You know, a fuel which is initially at room temperature, if we drop it into a furnace, its temperature will rise, it will catch fire, and some combustion reactions will take place, and so on and so forth. So all this combustion phenomena is actually an unsteady state phenomenon. So things are changing with time, and they are changing with time very quickly. For example, the entire combustion of a small piece of coal will finish in a few minutes. So that rate of change in temperature is quite high, and therefore the unsteady state conditions will come into picture. So in some conditions, as I said, time dependency is there anyway, and we can't avoid it, and therefore we have to study the unsteady state heat transfer. But as you can understand from intuition, you can understand that the unsteady state heat transfer is actually a little bit complicated than the steady state heat transfer. Why? Because if you this equation, this is one-dimensional steady state without heat generation, without transient term. But if you consider the transient term, you will have one extra term on the right. So in these partial differential equations, the more number of terms, more difficulties you will face for solution. Therefore, the unsteady state is a difficult problem to solve, but there are ways. We'll see, or we'll study what they are. Such unsteady or transient problems arise when boundary conditions change. So you see, we are doing experiments in the lab. We are doing the experiment in the lab at a steady state. And we must have observed that most of the time we are not changing the voltage. So for a particular experiment, if we set the voltage at 50 volts, we are leaving it at 50 volts because if I change that 50 volts to 70 volts, it will take about 45 minutes to reach another steady state or more than that also. Therefore, in a class of 1.5 hour duration, it is not possible to do this because the problem actually becomes transient before it reaches the steady state. Therefore, the transient conditions will be coming into picture, and therefore I'm trying to avoid that by not changing the voltage. So here the transient state continues until the steady state is attained. So between that time is equal to 0 to time is equal to 1.5 hours, that period is the transient state. But after 1.5 hours, it will reach a steady state. For example, a hot metal billet exposed to cool air. So this is a typical example. You have hot metal billets cast in a furnace, and let us say in an extrusion plant, and then you leave it in open air to cool. So initially, if it is a aluminum billet, it will be at a temperature of the molten aluminum is 650 degrees Celsius. The billet temperature could be about 250, 300 degrees Celsius, and the ambient air is at 30 degrees Celsius. So from 250 degrees Celsius to 30 degrees Celsius for that billet to cool, it will take about 8 hours to completely cool down. So but if you are not using any fan or any other external device. So this 8 hours is a transient period. So the boundary conditions are changing. Okay, because of that, we have a transient situation. The problem of a transient heat conduction is to determine the temporal temperature distribution and heat transfer during a given interval. Now look at what how the questions can change in a transient problem. If until now we have seen the steady state problem, and the question asked was what is the heat transferred and what is the temperature at a certain point. So we need the temperature distribution or spatial temperature distribution, and we also wanted the heat transfer rate after the steady state is reached. Now, when we come to this transient heat conduction problem, the question is temporal temperature distribution. Temporal means something related to time. So time dependent temperature distribution. So at a given time is equal to 10 seconds, there can be a certain temperature distribution. At time is equal to 20 seconds, the temperature distribution can change. And remember, the temperature distribution is now changing both with respect to time and space. Therefore, in this equation, if we include the transient term on the right side, then what will happen? The temperature is now a function of R, which is space, and also on the right hand side, we have the time temperature as a function of time. So now the temperature is a function of both time and space. Therefore, it is a partial, what the equation will become a partial differential equation. We cannot write no more, we can no more write it as a d by dr. We should write it as a dou by dou r only, because now it is a partial differential equation. So, but anyway, we have to find out the spatial as well as the temporal temperature distribution in a heat transfer, in a transient heat conduction problem. Types of, and also other question is heat transfer during a given interval. So in 1 minute or from t is equal to 0 to t is equal to 5 minutes, what is the total heat transfer? That is the type of question. Okay, from time is equal to 5 minutes to from time is equal to 7 minutes. What is the heat transfer? So that can be a different type of question. So in this way, you will have different questions in the transient conduction problems. The transient conduction problems, again, depending on their complication, depending on the nature, they are categorized as three different systems. One is called as a lumped system, other one is infinite bodies, and last one is a semi-infinite bodies. So for this class and for today's and the next class, I will talk about this lumped system. Infinite and semi-infinite bodies we'll see later on. as you see, as you can understand, lump system is the simplest of all the three. So lump is simplest, infinite bodies and semi-infinite bodies. They are complicated with the almost same amount of complication, but you should be able to distinguish between what forms a infinite body and what forms a semi-infinite body. So we will see that in detail after Cat 1. But let us now focus on lump system. Now you are familiar with the English word lump. Lump means something, a good amount of quantity brought together into a small volume. So that is called as the lump. Okay, it's not loosely left. It's something densely packed. That is a general understanding when somebody says a lump. A lump of clay means the clay is not loose. It's actually brought together and tightly packed. So systems which are tightly packed, which have a high density and which have a less amount of volume, they come in the category of this lump system. So let us see, before going to the lump system, we shall see what are the methods of unsteady state heat transfer available. So what are analytical methods are there? They are mostly available for lump systems only. So in lump system that we are going to see, we will apply the analytical methods because it is the simplest one. One-dimensional system or simple 2D systems can also be solved using analytical methods. So there are analytical solutions, but that they are quite complex. I will show you later on. One-dimensional system and simple 2D systems also have some analytical methods, but the problem is they are mathematically involved. So as you can understand, these are partial differential equations, and solving partial differential equations is time consuming. Therefore, we have time consuming. It's also difficult, and sometimes it may be impossible. So that is mathematically quite difficult. Then comes the numerical methods, which are like very fundamental methods and very powerful methods. They simply bulldoze their way towards the solution. Okay, they use the brute power of the computer's processing power and obtain the solution. So they simply bulldoze their way. That's the word used. But it is a slow process, and it's not exactly the most accurate. But for engineering applications, it is that accuracy whatever you get is quite sufficient. So numerical methods are applicable for any type of problem. So they're quite general. You can use them for any type of problem. See, we have solved one problem on heat conduction using the flux plot in the first problem we solved this morning. So that also can be solved using this particular method. It's easily extendable to multi-dimensional problems. So all you have to do is use a graphical interface and create the geometry. Depending on whether your geometry is one-dimensional or two-dimensional or three-dimensional, you can actually modify and extend the study. Then the knowledge of programming is required. If you are not using a package like Fluent or ANSYS or anything, then you will have to program it on your own. So there you will need the knowledge of programming. Where you need the programming is, firstly, you need to split the domain into a certain matrix, certain small control volumes. So there some programming is needed. Then after applying the concepts of heat transfer, after applying concepts of energy conservation, you will end up with equations. Those equations, for a small geometry, those equations can be a few hundred, and for a large geometry and for a large number of nodes, that equations can be few million of equations. Now, once you have these millions of equations with millions of unknowns, you should be able to write a program to solve those equations. Okay, so that those equations can be linear equations, they can be non-linear equations. For linear equations, that certain simplicity to solve is available. For non-linear equations, you may need to go for some special methods of solving. So ultimately, numerical methods are good, can be applicable for any problem, but you need to know the programming language if you are using a programming language and not a package. But if you are using a package, which most people do nowadays, like use the Fluent or OpenFOAM, which is a free software available. So using these packages, you can actually solve the problem without actually knowing anything about the programming, because the solution part is included in the program itself, in the package itself. Okay. Now, these are the methods available for solving a transient problem. Now coming to the simplest of the transient problems, what is called as the lump system. So what is this lump system? A system where the temperature of the solid is spatially uniform at any instant. That is called as a lump system. Spatially uniform at any instant. Now you see here, there is a copper ball. In a copper ball, now copper is a good conductor or a bad conductor? Tell me. Copper is good conductor or bad conductor?
Good conductor, sir.
Is a good conductor. What's its conductivity? It's about 300, about 300 watt.
400, no?
So among the commonly used materials for engineering purposes, copper is used where you need very good conductivity, but copper's weight is more and it's expensive. Aluminum is sometimes used. Aluminum has a lesser conductivity, but it is light in weight and it's also cheap. So depending on what quality you are willing to provide, you will opt for that appropriate material. Anyway, now see here, this is a copper ball and you see the temperature inside at different locations. It's all 70 degrees Celsius. Now look at this roast beef here. So this is a piece of meat and in this at different locations if you measure, you see here the most likely this roast beef is being probably roasted over over a flame. So at a particular instance the surface will be hot because it is closest to the flame, but interiors are still cold. Now whenever you are dealing with cooking of food, especially meat, you have to make sure that you get rid of the bacteria. The bacteria must be killed first, and it's generally understood that at 70 degrees Celsius, all the bacteria gets killed. So you have to make sure that all the temperature reaches 70 degrees Celsius to the core. So every part of this piece of meat has reached a temperature of 70 degrees Celsius. So when you measure this at this instance, you see surface is at 110 degrees Celsius and the center is close to 40 degrees Celsius. So you need to still heat it. But the point what I'm trying to you to notice is that you see there are temperature differences in the same meat. At the same meat, at one point temperature is high, other point temperature is low. But whereas in the copper ball, at any point the temperature is the same. So this is the difference. This is the difference. In a lump system, the temperature inside will be the same. And when the temperature is same, what happens? There are no thermal gradients. Thermal gradients means delta T divided by delta X. If I try to measure the thermal gradient between this point and this point, delta T is 70 minus 70 divided by this distance. 70 minus 70 is 0, therefore the thermal gradient is 0. So whenever we have the 0 thermal gradients, then we have a lump system here. Now this, let us assume that this is at T is equal to 20 seconds. At T is equal to 20 seconds, this is the situation. Now at T is equal to 50 seconds, now let us say this is inside an ambient temperature at 20 degrees Celsius. Now after some time this will cool down and now the system will have temperatures after 20 seconds. The temperatures can be, I mean after T is equal to 20, T is equal to 50, that means 30 seconds. After 30 seconds time, the temperatures can be 40 degrees Celsius, 40 at different locations, 40, 40, 40, 40. That means the temperature is changing with time. Okay, but within the body, the temperature is uniform. Do you understand this difference? So what property of the material can lead to this kind of a uniform temperature inside?
Sir, homogeneity
Sorry?
or homogeneous?
Homogeneous, okay, roast beef also is homogeneous, more or less it is homogeneous, let's assume. So leave that homogeneity apart. What else? What about conductivity, thermal conductivity? If the thermal conductivity of the material is good, that means if the thermal conductivity is good, that means the material has got a low thermal resistance. In such a case, there is a possibility of having this uniform temperature distribution throughout. So that word uniform temperature is important. All over the place, the temperature should be very much same. Heat conduction in the absence of thermal gradient implies infinite conductivity. So these are some things which have infinite thermal conductivity. This ideal and also infinite conductivity is impossible. This ideal and impossible situation can be approximated if the conduction resistance is low compared to the convective resistance. You see here, this object is having a certain conductivity inside, and also it is having a certain convection at the surface. So there is a conduction resistance inside, R conduction resistance inside, and outside there is a R convective resistance. So if this convection resistance and conductive resistance, if you compare them, if the conduction resistance is low compared to the convective resistance, then this is a possible system. The heat conduction equation cannot be used to solve such problems. So in this problem, this kind of a lump system problems cannot be solved using the heat conduction equation. So for that, we will have to apply a different method. So you see here in this figure, we have some object at initial temperature is outside. It's at a high temperature. Now it is dropped in a liquid. So what happens after some time? Its temperature keeps changing. What happens is it loses its heat from the surface to the medium, but within the body there is some conduction also taking place. So that principle we will have to use. So whatever energy balance we can perform across this surface, that will be used to come up with certain equations. Now you see here the analysis of the lump systems. The lump system can be analyzed using the energy balance. You must have seen this energy balance while you were studying thermodynamics. Energy in a control volume. Energy in a system, energy in minus energy out plus energy generated is equal to the energy stored. Okay. Now in lump systems, see, whenever we want energy generation, we are either talking about a exothermic chemical reaction or electrical conduction. Okay. So when in the absence of those things, the energy generation will be zero. So we will have only energy in minus energy out is equal to energy stored. Now you see here, when you drop a hot piece of metal in a liquid, the energy is actually leaving the surface because heat energy transfers from high temperature to low temperature. So heat actually transfers from inside to outside. So this term E out will be there. E in, nothing is entering. So E in will not be there. So E out will be there. EG is gone. So EST only will be there. So E out will be there. EST will be there. That means energy out should be equal to the energy stored. So minus of energy out, this minus sign is carried as this. Minus energy out is equal to the energy stored. So this energy stored is represented as, see this dot, the dot is the rate of energy stored. That is represented with the differential d tau. Tau stands for time. So change in energy stored with respect to time will represent what is the rate of energy storage. Now E out, the energy out, you see here the energy is going out of the control volume due to convection. So we read the convection heat transfer equation here, HA delta T. So minus HA delta T is equal to the energy stored. Energy stored, you see here, this is a certain, having a certain mass. So energy stored can be written as MCP dt. You are familiar with this formula, MCP delta T, isn't it? So a modification of this is if we introduce this delta T, the change in temperature with respect to change in time. So this is the accumulation term, or this is the storage term. So MCP delta T by delta tau, or MCP dt by d tau. So this dt by d tau is same as this one. And what is M? M is the density multiplied by the volume. And CP is C. So this M is this rho V and CP is C, and dt by d tau is nothing but delta T by delta time. So you see we have equated the heat convected to the heat stored. From this we can try to solve it. You see there is this term dt by d tau. Now this equation is same as the previous equation that we have seen. So this is dt by d tau. So now we always go for this non-dimensionalization. So this theta is a new term defined as a temperature minus T infinity, just for the sake of convenience. So dt by d tau is d theta by d tau. So this is written as a d theta by d tau. So now rho Vc rho Vc by HAS. HAS, this is HAS, we'll bring it to the other side. Rho Vc HAS d theta by d tau is equal to minus theta. Okay. This T minus T infinity is theta, so that minus theta is there. So now this is a differential equation. So to integrate this differential equation, we will have to solve it. We have to integrate it. So assuming this rho, volume, Cp, h, and area are constant, we'll bring it out of the integral. So we will have this integration from theta I to theta. So this integration is carried out with respect to d theta. Therefore, we are integrating between initial temperature to a certain temperature is equal to integral of minus theta. So this theta, this minus theta is brought here and d tau is taken to the other side. So integral d tau. And since this is time, we integrate it from 0 to certain time. So on the left hand side, the integration is from some initial temperature to an unknown temperature. And on the right hand side, we are integrating from initial time to some unknown time. So at this time, this should be the temperature. So what is the relation between this theta and this tau? So that we should evaluate. So if you carry out this integration, we know integral d theta by theta is a log of theta, log of theta. So you substitute this values, you will have log of theta I by theta minus, and then you have this integral 0 to tau d tau is this tau. Okay. Now you see, you separate it out. Log of theta I by theta I, you take this term to the right hand side. You will have this. You simplify this here, theta I by theta. That means this is log to base e. So this e will go to the right hand side. E power HAS by rho Vc tau, or theta by theta I is, which is t minus theta is basically t minus t theta. Theta I is ti minus t infinity. So you have this equation. So using this equation, you will be able to find out the temperature at inside a lumped system at any given time. So this is the time and this is the temperature. So if you know the initial temperature, if you know the surrounding convection temperature, you know the heat transfer coefficient, this and this, you will be able to find the temperature distribution. And also, we can find the heat transferred in a given time. Heat transferred is Q. Q is integral between certain time. So initial time 0 to certain time, integrate Q dt. Q is HA delta T. This is the convection heat transfer multiplied by dt. So you solve this and you will get this equation. So we came up with some equations. Okay. So this is one equation, looks simpler to estimate the temperature at any given time. And this is the equation to calculate the heat transferred in a given time span. Okay. So this is the interpretation of the lump system. The difference between the solid and the fluid temperatures will decrease exponentially to 0 as the time approaches infinity. So you can see here on the x-axis you have time, and on the y-axis you have this non-dimensional temperature. So you can see as the time increases, the temperature of the system, of the lump system, is approaching the temperature of the medium. So we will see, we'll continue this in the next class so that you will understand this. Okay. So I'd like to stop. We'll solve a problem. See, first, initially, this concept may appear to be difficult to grasp, difficult to understand, but it's a quite interesting concept and quite useful also. Many problems can also be solved. For example, earlier days when we didn't have the advanced forensic technology like we have it today, earlier days, this method of lump system was used to determine how long it has been since a person died. We know that when a person dies, the body cools down, the body temperature drops. So how long it took for the body temperature to drop to the current value? Initial temperature is, let us say, 37 degrees Celsius. The current temperature is, let us say, 25 degrees Celsius. So from 37 degrees to 25 degrees Celsius, how long it has taken to drop? that how long can be estimated using the equation that we just derived. So using that how long we can determine when the death took place. So in case of murders and so on, this method was used. Even though it was not very accurate, it was the only method available. So that method is actually based on the principles of heat transfer. Okay, so it has got quite interesting applications which we shall see in the next class. So now let me take your attendance. Mrutunidhi,
Present, sir.
Vilash,
Present, sir.
Ancharian,
Present, sir.
Madhusudan,
Yes, sir.
Philip,
Sir, Pranadri present, sir.
Siddharth,
Present, sir.
Vatsan,
Present, sir.
Maitreyan,
Present, sir.
Ranivel, Ishant,
Present, sir.
Milalagan,
Present, sir.
Niranjan,
Present, sir.
Karan,
Present, sir.
Abhijit Menon,
Present, sir.
Pratik Krishna. Pratik Krishna, what happened? He is absent since 3 classes. Praveen,
Present, sir.
Adil Sinju,
Present, sir.
Chaturvedi,
Present, sir. Present, sir.
Hassan, Ayush Tripathi,
Present, sir.
Harshavardhan, Hemant Kumar,
Hemant, present, sir.
Pa,
Present, sir.
Chandramouli Singh,
Present, sir.
Sairav, present, sir.
P. Raman,
Present, sir.
Al,
Present, sir.
Ish, Venkat,
Yes, sir.
Present, sir.
Pranav,
Present, sir.
Jayanti,
Present, sir.
Iniket,
sir.
Udri Narayanan,
Present, sir.
Vito,
Present, sir.
Ajit,
Ajit present, sir.
Ish Raghav,
Present, sir.
Ul,
Present, sir.
Rose,
Present, sir.
Ar,
Present, sir.
Karthik,
Present, sir.
Gauri Shankar,
Present, sir.
Ishwar, Jay Prakash,
Yes, sir.
Ka,
Present, sir.
Yes, sir.
Karan Sarvesh, Karan Ajay,
So Charan service present, so
Ajay, Benoit Simon,
Yes, sir. Present, sir.
Venkatesh,
Present, sir.
Jnanakshaya,
Present, sir.
and Dev,
Present, sir.
Varun present, sir.
Rao,
All present, sir.
Krishna,
Yes, sir.
Siddharth Madhur, Anand,
Present, sir.
Vani, Vasan,
Present, sir.
Narayanan,
Present, sir. Anish, present, sir.
Santosh Raj,
Present, sir.
Keshav Kumar,
Present, sir.
Akash Kumar,
Present, sir.
Karthik Prasanna,
Present, sir.
Sai Kaustubh,
Present, sir.
Aruna Halyan,
Present, sir.
Vesh Krishnan,
Present, sir.
LC Femina,
Present, sir.
Effort Gionel,
Present, sir.
Manoj,
Present, sir.
all the absentees once again. Palanivel, Kritik Krishna, Hamza Hassan,
Yes, sir.
Sri Kumaran, Motishwar,
Motishwar present, sir.
Charan Ajay, Vedant Madhur, Shivani, Kalai Priyan,
Chat box. Chat box.
all right. So we'll meet again on Thursday. We'll solve some problems on Thursday. We'll solve some problems on the lump systems. So your syllabus will be till that. You can leave the class now.
Thank you, sir.
Thank you, sir.